Okay, thank you very much. Good morning, everybody. Thanks for connecting to this course. Please, if you don't see me, if you don't hear me well, don't hesitate to stop me. In general, don't hesitate to interrupt, raise your hand, or they're not so many, so you don't even have to raise your hand. You can just turn your microphone on and speak up if you need to ask some questions, or if there's some technical problems or whatever. I don't know if you, I hope that you already met one another in some ways, even if this year, obviously, we have all these technical problems and cannot be physically in the same place at the same time. But obviously, I hope that it will not be forever for the whole semester. But I guess I'll skip the presentations for today. I just introduce myself. My name is Boschi, and I am a professor in geophysics at the University of Padua. If you need to contact me, so just so that you're not too worried, I've ordered a tablet which should arrive soon. So hopefully by the end of this week, beginning of next week, we'll be able to do this in a more technologically advanced way. But for today, I just found a whiteboard that I'm going to use to communicate with you. So my name is Lapo Boschi. I hope you can sort of read it. And maybe the red one will work better actually. And my email address is my first name dot my last name at unipd.it. Okay, University of Padua in Italy. Okay, not very far from you if you are interested. I guess I hope you can sort of read it. It's the first time I do this in this way, so you know, we are all experimenting together, and it will get better during the semester. What this course is about is a course in wave physics, which can mean a lot of different things. And I would like to start off interactively with you. I don't know really. I mean, I have some ideas, but I can't say I have a very clear feeling of what your background is, what you know already, and what you expect to achieve with this course. So I would like to start with a question, and feel free to answer in the chat or to speak. What are examples of phenomena in nature that are called waves? You know, what in practice, before we start trying to give formal definitions, what can you just think, and I want to hear or read your answers now. Can you tell me phenomena in nature that come to mind? What's the first thing that comes to mind if I say waves? If I say a wave. Yeah, think about it. Some things are happening right now. You know, some of these phenomena are taking place right now as we speak, right? At least there are two types of waves that we are using in a sense right now. Yeah.
Okay, wave can be likened to a disturbance.
I can't hear. I couldn't hear you.
Wave can be likened to a disturbance. A disturbance.
Say again. I'm sorry. It's
Wave can be likened to a disturbance.
yes. So, but so okay. I like the word disturbance. Okay, so you have basically that's true to have, but my question, well, to have a wave, you have to perturb first of all a situation where you're in a situation of equilibrium. So you disturb it, and this disturbance propagates. That's correct. But what I'm asking right now is some practical examples in real life where you are experiencing something that you call a wave.
The seismics,
Yes.
the waves in the ocean.
Very good. So we have seismic waves. We have waves in sea, ocean, water in general. Yes.
String vibrations.
Say again.
String vibrations.
Yes. Very good. So mechanical vibration in general. Strings. Yeah. Of course, what happens when you hit a guitar string?
The sound.
Yeah. So what's the sound? Sound. How does the sound go from the guitar string to your ears?
Sound waves.
Yeah. So sound is so the string vibrates and you have waves that propagate back and forth on the string, right? But also the string, the vibration of the string is transmitted to the body of your musical instrument, which itself vibrates, and then that's built in such a way that the vibration transmits into the air, and then once it transmits into the air, it propagates throughout the room, and everybody can hear your music. So there are two ingredients here, okay, to create musical sounds. You have mechanical waves in the instrument, and then you have sound waves in air. Okay. So it's funny that, but actually I'm happy. But I was expecting you guys to say right away light, right? I mean, there are also electromagnetic waves, but I'm happy because this course, as I'm sure you imagine, is not about electromagnetic waves. The maths of electromagnetic waves and sound or seismic waves is very similar, and you should think as you study acoustics or seismology that in the like most of what we do, of what we study, has actually been developed by people in the 19th century. People like 18th or 19th century, people like D'Alembert, Fresnel, Young, and so on and so forth. You will hear this name all the time, right? The Fresnel zone and the D'Alembert solution to the wave equation and blah, blah, blah. And these people were actually studying optics. And in the old days, actually, people didn't think, well, people didn't exactly know what light was, right? Light was a very mysterious thing, but some people thought light was made of some sort of particles emitted by a source of light, and that would hit your eyes and then interact with the nervous systems, whatever. But light in the old days was thought of as some sort of propagating particles. And today, this sounds very weird. And you don't want to tell my colleagues that Professor Boschi said that light is made of particles. That's not true. Today, we know it. But in the old days, Newton, of all people, thought that that was the case. And a whole other class of people thought instead that light would propagate just like sound. That light was a wave, okay? Light was a disturbance that propagated without displacing the actual matter, without moving the matter around other than a small vibration in place. And they thought that the medium, okay, just like sound propagates in air and seismic waves propagate in the soil, in rocks, early physicists like Huygens, we speak about him in a minute, thought that there was some sort of invisible, or I should say, imperceptible medium, imperceptible substance distributed everywhere in the universe that they called ether or ether. I'm not sure how exactly it's pronounced. That it was a mechanical medium, like a form of matter through which this mechanical vibration that they thought light was would propagate. And this idea survived until I think towards the end of the 19th century, the mid 19th century, let's say, until I think, well, I cannot really give you an exact date because I don't know it, but the point is that for a very long time, people thought that not only mathematically, but even physically, sound and light were almost two forms. Sound and lights and seismic waves were three forms of almost the same thing. So in the future, I think I'm insisting on this idea right away because you will be confused otherwise. I think in the future when you read books on waves, and you will find this constant confusion between optics and acoustics and seismics. Okay, the math is almost the same in many ways, as you will discover. And the physics in the old days, people thought it was also almost the same. Today we know that electromagnetic waves are a completely different beast because they are waves that there's a propagation of energy without moving matter around. Okay, so in a sense, today with quantum physics, we almost think that Newton was right and that the propagation that light resembles, a quantum of light resembles a particle much more than anything else. But that's all I'm going to say this semester about electromagnetic waves. Okay, this course is somewhat optimistically called wave physics, but it should probably be called elastic wave physics or mechanical wave physics or acoustic wave physics, and you should be aware of this difference. So you already basically went ahead of me. One of you did, and you mentioned, and you mentioned that you started to try to give definition of a wave, which sounded okay. Let's think about it a bit more. What happens when, we all use the word wave, right? More or less knowing what that means in practice. But let's try now to be a bit more scientific and give a definition, a rigorous definition that can be verified experimentally. So what's the mechanism of the propagation of a wave? What happens physically when a wave propagates? some of you started to give an answer, okay? There, you imagine that you start with situation, you know, what in physics we call equilibrium. You know, so nothing's moving. Everything is at rest. Then we perturb or disturb this situation, and then what happens? Why do we have this propagation of a vibration? I'm not, when I ask these questions, you should know right away. I'm not expecting one of you to stand up and give me like a dictionary definition. I just, what I find useful is for you to shoot out some keywords that then we will elaborate together. So what I'm trying to do now, I'm not trying to see how smart you are, which I'm sure you're very smart, but just trying to probe your existing knowledge and attach myself to it so that I have some hope of making sense to you. So that brings me to my questions. To my question, if I ask you what's a wave, like how would you start to give an answer to this? Maybe you remember some theorems, some.
Like energy is transferred.
Say again?
Energy is transferred.
Energy transfer, yes. Wave is at the, okay, one of you, yeah, energy transfer, very. And wave is a disturbance that travels through the medium. That's very good. I also like surf. Yes.
We can also say that is a mass transfer.
Mass transfer. Okay, mass transfer is I'm not. Yes, I think. Well, for now, I'm just going to write everything that I hear, and then we talk about it. Wave is a disturbance that travels through the medium. That travels through the medium. So, yeah. Okay. So basically, to me, if I understand correctly what you said, that was Newton's idea. Newton's idea of light is that a light bulb, for example, is something that shoots particles, it shoots matter out. So light is some sort of weird substance, well, not weird, but it's some sort of substance that you can't really weight or touch, but that's probably maybe because the particles are too small or too whatever. But when it hits your eyes or some material that's sensible to light, some instrument that can somehow measure light, then something happens, right? So today we don't think that this is quite right, or in any case, we wouldn't probably put it this way. So we would rather say that a wave is energy transfer without mass transfer. To me, like one way to think about it is imagine that you are on the beach and you're watching some buoy, you know, some floating object like a ball, soccer ball floating a few meters away from the shore in the water, okay? So when a wave comes in, usually the ball doesn't usually come to you unless it's already really close to the shore, but it just stays there. It comes a little bit towards you, then it goes back, and then it comes towards you again. Yeah. And so on and so forth. Okay, so it moves horizontally and vertically a little bit, but it doesn't just come to you. So another way, what comes towards you is the crest of the wave. Okay, so this disturbance actually travels towards you, but this disturbance, doesn't move the mass around. It doesn't mean that the water that now is the same molecules of water that now are 1 kilometer from the shore will actually hit me in a few minutes. They more or less stayed there, okay? I mean, of course, in the ocean, there are also currents, so it's more complicated than that. Or maybe even better, think of sound. If I speak, my vocal cords vibrate. And now we are not even in the same room, right? But if you were in the same room, what happens is that this vibration travels through the air. The particle of air that I set in motion through my mouth hits the next particle, which hits the next particle, which hits the next particle. This goes at a speed of 300 meters per second, which depends on how dense air is at atmospheric conditions and how heavy a molecule of air is, and so on and so forth. But you know that this speed of sound is more or less constant, and eventually this vibration, like the next particle hits the next particle, hits the next particle, until the particles that are inside your ear are also moved around, and this vibration then is recorded by your cochlea. Okay, so for me to speak to you, even when we are in the same room, I don't need, there's no transfer of matter from my mouth to your ear, luckily. This would be very bad, particularly these days. There's only a transfer of energy. And the physics, the properties of nature, of matter, are such that this disturbance travels from my mouth to your ear, keeping the same shape. Okay, if I say surfboard, and you're sitting in the far end of the classroom, and maybe you will hear a bit of echo, and maybe the sound will be attenuated because you're very far, but you still hear surfboard. Okay, so that means if we all accept that what we are observing is a wave phenomenon, that means that what we are observing, what we could use, what we could say to define a wave, is that a wave is a disturbance that travels through a medium, keeping its main properties constant. Okay, we will speak of frequency later, so I don't know how well the concept of how clear the concept of frequency is for all of you. Probably very clear for some, a bit more difficult for others, but basically the frequency of the sound stays the same, okay, as the sound propagates. If I speak, if I say some very grave words, you still hear it very, very grave, very bass, and if I emit some acute, some very high-pitched sound, you will hear high-pitched sounds, and so on and so on, and so on and so forth. No matter how complex, how much echo you might have in the room where we are sitting. Okay, which is a consequence of the physics that we will learn in this course, and is the reason why we are able to communicate, to use sound to communicate with one another. Okay, our goal here is not just to stop at sound propagation in relatively simple media like air and water, but we want to eventually, I erased it, but eventually we want to get to seismic waves, which are a bit more complex, because sound, when sound propagates, it's just a compressional wave. So it's just the pressure, the disturbance that we talk about is just a change in pressure, which is the same independent of the direction. With seismic waves, you have a combination of pressure and shearing, okay, of friction. And that mathematically is more complicated. So eventually, if I'm fast enough, we eventually will get to that, and then you will be ready to go into seismology and seismics in the rest of the semester. So I didn't touch on one of your suggestions, which I like, surf. So surf is actually a very a somewhat confusing phenomenon to think about when you think of a wave, because in the case of surf, you actually have transfer of matter, in the sense that your surfer, okay, the surfer rides the wave, right? So if the surfer is good, what the surfer does is he or she manages to follow the crest of the wave as the crest of the wave propagates. I don't know how precisely that's done, because I've never even tried. But what we see when we look at these people is that, you know, the wave moves. So that's not a translation of matter. It's just a translation of this disturbance, right? That moves across the ocean. Okay, so this guy just goes up and left and right a little bit. This guy goes down, then up, then down. These things moves. Matter, I insist, is not translated. But the guy with the surfboard manages to always stick to this point of the wafer, okay? So in that case, you do have a transfer of matter, but the surfer is not, the surfer himself or herself is not a wave, he's a surfer. So think about it, okay? But it's good that you mentioned that, because it's an interesting experiment to think about. I think that well, no, I'm not. That will be your homework for, not for Wednesday, but for whenever you want, and then you can come to me and tell me what you found out. The physics of so it could be a good term paper if you have to write term papers. That how does surf work in terms of physics? I don't know, and I'm not going to try to give an answer now, but I will think about it myself sometime. So now
Actually, hello. Actually,
yes.
sir, kindly repeat your question.
Yes. Oh, repeated the question. Sorry, I thought you wanted to ask a question. The question is, Google surf physics and try to understand why that guy manages, how those guys manage to go from somewhere in the distance to closer to the beach. I think they actually, the truth is that they don't move that much themselves. They move more like along the crest than towards the beach. So probably they don't move in the direction of wave propagation, but rather transversely. But I'm not sure. So question, Google this and figure out what physically a surfer does and how he or she achieves this.
Okay, thank you.
Yeah, thank you. Okay, now I'm sort of, one of my problems as a teacher is that I have sometimes a tendency to wander away from the topic of my lecture. So let's go back to our more serious endeavor, which is to like to get to the mass of waves, not just the phenomenology, but also the theory. And now the question that I've just asked actually was a way to get to a fundamental, well, something that we still consider, even though it's very simplistic, but we still consider it a fundamental insight in wave physics, the Huygens principle. Okay, so Huygens is the name of a Dutch physicist who is more or less contemporary of Newton. So we are talking, I sometimes get these things right, but we are talking 17th century physics, right? So ideas about waves and light and sound are still very open, because the technology to do the experiments that we are aware of today were not available at the time. So people have been much more creative. Newton had this idea of light as a transfer of matter. Huygens, he was on the opposite side of the spectrum, and he thought that light was a wave, and he presented his idea of what a wave, of what does that mean, light is a wave, okay? So he presented this idea, and he thought of matter, which meant air, which meant water, which meant rock, which meant also ether, okay, at the time, as how can I say, a set composed of a lot of particles, of molecules sitting next to one another, okay? So if one of these little parcels, these little particles of matter moves around, if we disturb it, as you said, if we perturb it and set it into motion, as it moves, it necessarily hits the other particles that are around it, right? So in so doing, so those particles initially think, what happens if those particles start out from a state of equilibrium? When you hit them, when the first particle hits them, they start also to move it. You know what happens if you throw an object against another object. Some of the kinetic energy gets transferred from one to the other, and so the second object will also move a little bit, and in so doing, it will touch the neighboring molecules, which will also start to move around. So I guess for us today, this is absolutely obvious, but at the time of Huygens, probably it wasn't. And so the way Huygens stated what is now called Huygens principle, is perhaps a bit difficult for us to initially to understand, but basically I think that it was just a way of describing this phenomenon. Huygens said that every point in space that receives a wave becomes a source for another wave. Okay, this is not I'm improvising a little bit there. I'm not copying like the exact words that Huygens said or the words that you would find on Wikipedia. I don't care, you know. I mean, the point is that you get the idea of what he of the way he was thinking. Huygens' principle, even in its most perfect, even if I use the exact word that he said, Huygens' principle is not exactly right for reasons that we will see later today, although the underlying idea is essentially right. I mean, if you have a medium, which indeed is made or can be thought of as an ensemble of particles of matter, if you hit it in one point, the molecule or the set of molecules that you hit will perturb the molecules that are around it, and this effect will propagate. Okay. Have you do people still teach these things? I mean, have you heard of Huygens' principle before? Yes, no, maybe you don't, maybe, but you don't remember. You seem like you're thinking about it.
Yeah, hello.
Huh?
Yeah.
Yeah, it does strike a bell. It's not the first time. Okay.
Yeah, it's not the first time. I've heard about it before.
Okay,
cool.
good.
Yes.
So, yes. So the difficulty with Huygens' principle. So in a way, Huygens' principle, in many courses in wave physics, it's like that's the starting point, and everything is built upon this idea, more or less. I'm not like I like to explain what Huygens' principle is, and you should understand it. You should be aware of it. But of course, I also think you should be aware of the fact that there are many difficulties with it. One, like compared to, see, maybe, yes, there are two things that I want to tell you about now on the basis of Huygens' principle. One is interference. And the other is diffraction. Okay, in a way, we start out with relatively complex ideas, but when we go back and start doing the math, things in a way will become easy again. But I would like to give you this initial overview of some concepts that are very important when you think of waves. Can any of you, or all of you, or some of you, try to give us some idea what interference is as a phenomenon related to waves? Again, I'm not expecting a formal definition, just so try some, give me some keywords. Like if you think, if I, like, free association in psychology, if you If I say interference, what do you think about? Maybe, you know, no, I'm not going to help you yet. Yes, very good, very good. So waves that superimpose, waves that combine to give a resultant wave. So basically, wave phenomena are linear in the sense that if you have, instead of one source, you have two sources, the disturbances that are associated with each source, they sum up linearly. But what am I trying to say with that? Imagine, okay, that you do an experiment where you measure elastic waves. You know, you have, imagine that you put some sensors of vibrations on the table where you're working, and you hit the table in one point and you record the vibrations at two different receiver locations, okay? Then you hit the table at another point, different from the first, and you record again the vibration at the two receivers. You have pairs of seismograms. Actually, to be honest, to do this experiment, sorry about that, one receiver is enough. So let's start again. Throw away the first receiver, throw away one receiver, keep just the other one. Hit the table at one point, you have one seismogram. Hit the table at another point, you have a second seismogram. Okay. Now you hit the table at the same 2 points as before simultaneously. Okay. What you get is a third seismogram. That third seismogram, it's exactly the same as you would obtain by summing the first two. Okay, so let me show it to you on the whiteboard. So here's my experimental setup. This is a plate of some kind. And here I have a receiver. Okay, you will have to get used to these words: source, receiver. A receiver, you know, a receiver means that it's an observation point or it's an instrument that can record vibration. In seismology or acoustics, you always record vibration. It can be a change in pressure or a displacement of the ground, whatever. We call it receiver, okay? So in this course, a microphone is a receiver. A seismometer is a receiver. Accelerometer, whatever. Okay, so here is our receiver. In this case, in experiments that we do in theoretical, you might call it laboratory seismology or physical acoustics, these are piezoelectric sensors that we stick to our plate. Okay, usually we do, I personally have done these experiments with aluminum plate. And then here you have a source, okay? A source is anything that determines a displacement of your medium, okay? A speaker meaning a loudspeaker, is a typical source in an acoustics experiment, or a vibrator that sets this plate into vibration. That would, an earthquake is a source, an explosion is a source. So we always use this word source, okay? Something that generates, that emits vibration. Okay, this source one emits vibration that propagates around the plate. And we record it at the receiver here, okay? Okay, this is my poor rendition of a seismogram, quote unquote, because this is not the Earth object, but acoustic recordings or recording of a vibration. Okay, then, so that's my first experiment. Then I deploy another source at another location in my medium, and that generates a second wave system that I record at the same receiver. This source is closer, so the first vibration will come in a bit earlier. Then I don't know what disturbance, what kind of wave I send into the system, but let's make some. Okay. So then I do a third experiment where the two sources are excited at the same time. But if I use my hands, I would just hit these two places of the boards at the same time. You know, if we do a real experiment, we are not going to use our hands, right? You would have some sort of instrument to generate vibrations always in the same way. And so now the point is that if the signal that you inject in the system is always the same, this is just the sum of recording 1 and 2. Okay, so this is a fundamental property of waves that you can test experimentally and that we will also prove mathematically. So the idea, of course, is that what I should also mention, insist on, is that when you do your third experiment, the signal that you inject here is exactly the same as in the first experiment. Have you guys followed this? Yeah, it's okay. I'm not offended if you say that it was a mess. You know, it's that's part of the. So, but thank you. I'm very happy if you understand. So why am I spending time on this? Because you were talking about interference, right? So now what Huygens says is that in fact what you observe when you observe a wave is the result of a lot of sources acting at the same time. Why? Because remember, what does Huygens say? Huygens says that like if I just hit my plane, you know, my medium, whatever that is, at one point, that's the primary source, but that will immediately give rise to a lot of secondary sources all around it. And so each of these sources will then give rise to more sources around it, and so on and so forth. Now, what Huygens cared mostly about, well, let's just jump to the conclusion of what is that if you also consider that that's interference going on, you have to think that what you observe is the sum of all this infinity of secondary wave fields that continue to be generated. And if you do the math, you will find that the sum looks just like this. Okay, you have just one crest, and everything else is a small negligible oscillation that you don't care about. And this, so what we are talking about here are two forms of interference: constructive interference. So in places where, where the crest of the waves arrive at the same time, you know, the crest of different secondary waves arrive at the same time, you have a crest that's bigger, that's twice as large as either one of the two contributing ones. So if you have even more than two crests arriving at the same time, you have a lot of constructive interference, and the signal becomes larger. But in places where that's not the case, or maybe, you know, if your wave has a positive and a negative, if it has a crest and a throw, then you either have no interference or destructive interference, and so nothing important happens. In this particular case, this particular very simple case, basically, everything would be approximately zero except for one crest. Okay, learn also these words that I'm using. Crest is the high point of the wave, is where more or less the surfer wants to be, more or less. And throw, the throw of the wave is the bottom of the wave, okay? Where you are sitting and you see the crest on top of it, okay? I'm almost sure that this is the correct spelling. Okay, so Huygens principle, if you just take it as it is, at least when I was first taught Huygens principle, I thought this doesn't make any sense, because, like, you know, a wave is such a simple thing. Why do I need 3 million sources all over the place? But if you think of Huygens principle and interference at the same time, then it starts making sense, okay? Huygens himself didn't, you know, these are the really early days. So Huygens didn't care about what happens behind the wave, right? So he thought, even without thinking of interference, it makes sense that a wave, so that it makes sense to think that a wave is never gonna get to an observer here before all the particles between the source and the observers have hit one another. That's essentially what Huygens wanted to say. He didn't care if then in the coda of the wave there's something going on, whatever. You know, he already wanted to explain the most macroscopic thing. But then there's another name that if you take a wave physics course, you probably should remember, and that name is Fresnel. Fresnel is a French physicist that came to the scene almost more than a century after Huygens. And Fresnel understood, was the first to understand. See, that's not my telephone. Fresnel was the first to understand the meaning, the importance of interference. So if you start looking at Wikipedia, textbooks, and so on and so forth, and you Google Huygens principle, what's gonna happen is that in some books, especially in French books, I promise you will find, instead of Huygens principle, you will find Huygens Fresnel principle, okay? Which is basically the Huygens principle that each point becomes a secondary source, plus Fresnel idea that if you want to use this to do some math, you have to, and you want to really sum mathematically the effect of each source with one another, you want to think of interference. You want to take into account another principle, that is that wave phenomena are additive. If you have one source, if you have two sources and measure the effect that they cause, you get the same result that you would get if you were to measure each source individually and then sum. Okay. So I'm not doing any math yet, but don't worry, we'll get to that. but I really, you know, this is not just trivial, basic sort of phenomenological description of what a wave is, but if you do seismology or acoustics for a living, you will find yourself for many years asking yourself what really does Fresnel, what really did Fresnel do? What really is the effect of interference in a lot of practical situations? Do you have, so I've been talking for almost an hour. Do you have any questions, comments, something that you would like to share, something that you want me to repeat?
Sure. Can you give me some books?
Yes, you know, I was thinking about it. So I can give you, see, I have to admit that this last few days I was preparing this course and I completely forgot that we should talk about books. Of course, it's not difficult for me to think of some books. See, there's one. So there's a lot of books in seismology. Obviously, we are doing this because you want to learn seismology eventually, right? So there's lots of books in seismology. In the end, like one book that I always, that's been around for 40 years, but I always find myself going back to it is Aki and Richards. Okay, so this is the classic seismology textbook. Okay, so I don't think it's the greatest book. It's got a lot of problems, but in the end, it's the most, I think it's the best of what's available. Let's put it this way. Okay, so Keiichi Aki, it was a Japanese seismologist who passed away, I don't know, 10 years ago or so. And Richards is
okay, sure. Okay, so I got it.
Okay, thanks. I was getting a bit tired. Now, if depending on, I'm here. Sorry, I'm going through my books. Yes. So then, depending on like how curious and how quick you are in reading things, I'm not very quick. So I think Aki and Richards is probably much more than I would be able to digest in a semester. And I think if you want to invest your money in a book and you want to be a seismologist or a geophysicist, that's probably your best bet. And I guess, you know, I shouldn't say that, but you can find, it's very easy to find. I mean, I suppose it's easy to find it on PDF online somewhere. It's easy to find it secondhand on Amazon or whatever. A classic book in geophysics, not just for seismology, or two classic books are the books of Love. Okay, this is Dover. Okay, so Dover are very cheap but very nice editions that you can easily find with Amazon or whatever. And these are the two books that Love wrote in his life. Mathematical Theory of Elasticity, it's basically, these are books that were written at the beginning of the 20th, so about more than a century ago, okay? A bit more than a century ago. So they're kind of old in many ways, but the truth is that the theory hasn't changed much since then. So what I teach, what you learn, what my colleagues teach around the world is based to a large extent in this book. I mean, several generations of geophysicists, either directly or indirectly, have learned these things. So today, with respect to our sensibility to 2020, this might feel a bit heavy. There's like a huge historical introduction at the beginning, and you know, lots of pages like that, you know, so it's kind of scary actually. But you have to think that you probably will never read, I have never read the whole thing. Like, I will probably in my lifetime, I will probably, it's kind of sad to say, but I will probably never read the whole thing, right? But there's a lot of stuff, you know, when I don't know where to look, I look here, and it's got the same explanation that my professor gave me 30 years ago, and you know, now I'm here and I say, oh, that's where he took it from. So love is like the Bible in some ways. Like, we don't read it, but we know it anyways because it's there floating in. So a treatise on the mathematical theory of elasticity, that's got a lot of all the stuff that you will see both in geodynamics and seismology courses, Navier-Stokes equations and constitutive relations. And the other one is some problems of geodynamics, which maybe that's a bit less important, but it's got, I mean, basically it's like, it's got a lot of very nice, yeah, it's just a great book, you know. So if you are really hardcore, you know, that's also, and there's a last book that's one of my, that's like my personal favorite, and if you read that, it kind of reflects the way I have tried to teach you this morning. So, you know, no math, but I get to the math later, but lots of phenomenological description of how things work and why. And that's Fundamental of Musical Acoustics by Benade, also Dover. Okay. So this book is great. It's called Musical Acoustics, but you know, it doesn't matter. Like the first 4 or 5 chapters, which I think are really great, they are just general acoustics, you know, they explain what happens when you hit this stuff that we will cover in this course. The vibrations of the string, the normal mode of oscillations. So if you read it up to chapter like 4 or 5 or 6 maybe, it has like a lot of material. If you understand it, it will help you a lot in seismology as well. I don't think I want to, for the time being, to recommend more than that. There are a lot of seismology textbooks, Lay and Wallace, Y Session, Udias, they're all kind of the same. There's one thing that I want to say about all these. When you think of books, like there was a big change in the way we learn and think about seismology and other fields of science in the last 20 years. Computers, more than 20 years actually, computers became very powerful, which means basically that when, you know, a lot of seismology and acoustics and applied physics is solving numerical equations, solving differential equations, okay? We will get this week, in this course, I will tell you from scratch what a differential equation is. I mean, probably you already know, maybe some of you don't, some of you know a lot about this, but anyway, a differential equation is a mathematical equation. And you know, in the old days, the goal when you were faced with a differential equation was to solve it analytically. Like if you want, the typical problem of a seismologist is we want to model seismograms, okay? We have a model of the Earth, and which means a set of functions, density, seismic velocity, rigidity, whatever, as a function of position in the Earth. And we want to mathematically obtain an equation that describes how a wave propagates into sorry, I just saw your question now. I will answer to that in a second. So in the old days, if you wanted to compute a seismogram, you didn't have a computer. The approach was, let's assume that the Earth is very simple. Let's assume that the Earth is a half space. Let's assume that the Earth is a uniform sphere. And let's do the math. Let's find an analytical expression for the solution of my differential equation in such a simple medium, okay? So it sounds easy, but that's actually very hard. Even for a spherical Earth, to get analytically to a formula for how a seismogram look like, it's very complex. And if you want to do a realistic Earth, if you want to think that there are continents, that there are oceans, that the crust has a variable thickness, that it's not a sphere, but an ellipsoid, and so on and so forth, it becomes basically impossible to do it analytically, to solve, to do the derivatives and the integrals analytically and come up with a formula, So in the old days, the approach was, okay, this is too hard, so I teach you to solve the problem by yourself in a simple medium. And maybe in 20 years, when you're old, you will be able to do it for a slightly more complex medium. Today, we don't think about it like that anymore, because to solve a differential equation, we just feed it to a computer. We do it numerically instead of analytically. And the computer, that they are so powerful today that compared to just when I was your age and I started my PhD, it's just unbelievable what you can do now even with a laptop, right? That you can carry in your pocket almost. So today we don't care so much about teaching people how to solve equations. Okay, I want you to understand what the physics is behind that equation, and what it means to solve that equation, what you do when you have a solution. But it's probably not so important anymore that you're really able to solve some incredibly complex differential equation with some weird boundary conditions and so on and so forth. You have to know what it means to solve a differential equation, but you don't have to do all the procedure yourself. You don't have to do calculations by hand. So why am again, I'm taking a big detour, but you asked about books, right? So the books like this, they're all about how to solve the problem. They formulate the problem in a simple way so that you can come up with an analytical solution, and then you interpret the physics that analytical solution contains. This is very important to some extent. Like, I think I will teach you, if I have time, I will teach you how Rayleigh, 150 almost years ago, proceeded in this way to come up with a formula for the Rayleigh wave, okay? And love, same thing, okay? It's kind of complex. It's all analytical math, okay? You do a lot of analytical derivation to come up with a formula. But like, I don't care if you're not able to do the same thing in a spherical Earth with laterally varying MOHO. That's not important. Once you understand what a Rayleigh wave is, then you want to model a Rayleigh wave in a more realistic medium, use SpecFEM, use spectral element, download the code and run it. Unless you want to be someone who develops the code, but then take informatics, So that then the difficulty becomes how to program, how to code, not the physics. After all, you don't feed solutions to a computer, you feed a problem, not a solution. So, okay. So why am I spending so much time? I think basically that books that were written roughly, I'm making like, I'm making a exaggerated statement that probably I shouldn't, but the way, at least just to give you an idea of how I would think if I were to invest my time in reading a book, the books that are written over the first part of the last century all the way to the 90s. So most of the last century, actually, they're all about finding solutions. Today, we don't care so much about finding solutions. We want to understand how the problem is formulated well. And maybe we want to learn to formulate new problems in the right way, okay? We are lucky today that we have computers that do a lot of the hard work for us, okay? So if you're looking for a book, see what's coming out in the market now. Like, I don't know what the newest books are. Or maybe go for the very old classic textbooks, you know. The stuff that came out in the 50s, the 60s, the 70s, it's very hard, and I think it's going to go out of fashion if it isn't out of fashion already. Okay?
Okay, excuse me, sir.
Okay, thank you, sir.
So you told about the differential equations. I am from a mathematics background.
Yeah.
I done my MPhil in mathematics. Sir, where we unable to find the exact solutions, mean analytical solutions. We applied some numerical techniques. Which numerical techniques we will be used to solve these models?
Okay,
Actually, I am working on some of these techniques, some of these numerical schemes, but which one we use in the Earth system models to get its solution?
that's a very good question, very nice questions. I'm telling you, you know, I'm not a numerical modeler. I'm a client, a user of these things. So I'm telling you what's on the market in seismology now. And basically the code that most of my colleagues in global seismology use is called SpecFEM. I'm going to type it in the chat, which means spectral elements, basically. I think I mean, I don't really remember all the details about this, how these techniques, I think it's a pseudo-spectral code. And it was developed, that there are a set of papers. The authors that you want to Google are Komatic and Tromp, not Trump, but Tromp, who wrote all the code and a few papers that describe it very well. I don't claim that that's the best way to go, but that's what, you know, it's sort of a common language in seismology now. Like, if you speak to a seismologist, chances are that they know where that is. Then there are the Galerkin methods.
Discontinuous Galerkin and finite element methods. I think you are talking about this one.
Yes, probably. If you send me the link, I can confirm. But you know, anyway, you know, just check if the developers are the main guy who ran the project is Jeroen Tromp from Princeton.
Repeat the name of that guy. Or send the name of that guy in the chat.
Yeah. The names that I have in my mind right now, oh, I see the problem. Wait. I'm not sending the chat to the right list. Everyone.
Okay, fine.
Everyone. So here we go. Now you should read. You should all be able to read my chats. So
yes, I got it. Thank you so much.
Sure. So I shouldn't spend too much time right now, because this is the kind of thing that we learn maybe, you know, a few months from now. But it's a good question, and if you want, it's good that you start thinking about it now. So in seismology, these would be the keywords that I would start with, and then of course, you know, ask my colleagues as well, because this is my answers, but it's a developing field. So
Okay, thank you so much. One thing more, sir.
yeah.
So you talk about the Navier-Stokes equation. Basically, is a generalized equation in the fluid dynamics.
Yeah.
So why we are unable to find the solution, general solution of that Navier-Stokes equation?
No, there are general solutions. I mean, there are general solution of Navier-Stokes, but you do it for, I mean, the way I see it from the applied point of view is we define the medium, the object where you want to apply that equation. So if you have okay, first of all, well, there are a few things that I need to say. So basically, I think the simple answer is that we can find solution in simple media always.
Oh yes.
Like if you limit the level of complexity of the medium, you will find a solution, yes. So if your medium is unbounded and uniform, there are solutions to all the relevant equations in acoustics and seismology. But the problem is that the Earth, ultimately, we care about the Earth, and the Earth is irregular in many ways. And most importantly, nowadays, it's really the irregularity. Like if you want to do research in seismology today, we know what a Rayleigh wave is, right? I mean, we don't care about the fundamentals. We care about what happens if the town of Trieste, is shot by an earthquake, right? Is my building going to collapse? Like if I live on top of the hill or in the sedimentary basin. So for that kind of stuff, you're not going to be able to find an analytical formula. You have to do some numerical modeling, okay? So
Yeah, thank you.
the Navier-Stokes, we will, I hope, like if I'm slow, if I continue to be slow like I was today, maybe we'll never get to it. But if I am a bit more efficient, we get to the Navier-Stokes equation, which is the mother of all equations in geophysics and fluid dynamics. Well, actually, no. What my favorite one is I think in most books, it's just called Navier equation. Okay, so, and that's the equation for an elastic medium. Okay, if the medium is not elastic, but it's more like fluid, then we call it Navier-Stokes. So if you take a geodynamics course, like flow in the mantle and so on and so forth, they speak of Navier-Stokes. In seismology, we really, unless we want to model waves in water, which I don't think I will, but I'm still thinking about it in this course. I mean, we don't get into Navier-Stokes. We stick to Navier. We'll get to this later. I mean, I shouldn't jump too much ahead of myself.
Okay, no problem. Thanks a lot.
One of you, so let me answer the other questions. One of you asks Fresnel principle. So Fresnel principle, I have to tell you, don't think too much, like depending on where you look, people will use the same name, the same word to refer to different things, okay? So you have to be very careful. Like there are some things, okay, that we all agree upon, like Navier equation, I think we all more or less agree upon. The Newton's laws, luckily that we all agree upon. But Fresnel principle, like, I don't think that's really necessarily the most standard way to refer to what I think this refers to. I think that what we want to, I think that it's probably safer and more general to call it Huygens Fresnel. And Huygens is the guy who said, if I hit my medium in one place, all the locations that are around that place become new secondary sources of the same disturbance. And this phenomenon is repeated iteratively until the wave that is so generated propagates across the medium, okay? So Huygens came up with the idea of secondary source, okay? Another way to state it is a location, a place that receives a wave automatically becomes a source of the same wave, of the same signal, of the same sound, of the same mechanical vibration. And Fresnel contributed the idea of interference to this. If the point that I try to make in this lecture is that it's very difficult, I think, to really understand, to really accept Huygens principles today if we don't combine it with the idea of interference, okay? Because otherwise you cannot really expect that this combination of a lot of sources that are generated through Huygens principle will give rise to a simple, coherent waveform. You know, what Huygens says is that basically when the classical example, right, you throw a stone in a pond, in a otherwise calm surface of water, mass of water, well, you see, it's just a super simple circular wave that propagates away from the location where the stone entered the water. According to Huygens, what happens is that that stone moved a lot of particles of water that became sources themselves. So you should see a lot of little circular waves all over the place, right? Each time a new particle of water is set in motion. But you don't. Why? Because there's interference. Okay? Because if things don't sum up, don't have the same sign, they basically, on average, they cancel each other. And so if you think that there are these two things going on, like lots of secondary sources, but with interference, then you can make sense of what you actually observe in nature. So this is a very, you know, I now that I know that there are mathematicians among you, I'm a bit worried about this type of explanations that I give. It's a very, you know, this is something that I could say to someone that has studied Italian literature, and hopefully they probably more or less understand. It's a very simplistic explanation, but it's the first time we meet, right? So I promise you that it will become more rigorous. Today, I just would like to make sure that we agree on some fundamental phenomenological ideas about what we talk about when we talk about a wave. The other thing, maybe to wrap up today's lecture, the last concept that I would like to introduce is that of diffraction. Diffraction. Excuse me. And so this is a very delicate concept to think about. And I think to understand why it has been so important to think of diffraction to understand that there is diffraction in wave propagation, we should probably think again in terms of this initial dichotomy in the study of waves between the corpuscular, okay, idea that's due to Newton originally, and the wave, the Huygens idea, okay? So these people were concerned about light for Newton. Light was made of particles for Huygens, light is a wave. So the experiment, and I probably will leave you to reflect on this thing that we should think about is perhaps could be as follows. Imagine, okay, that you have a harbor, okay? We still think of water. So here is the open sea. And then, so there are, and then you have a port which is, has a pier, two piers here, and some sort of entrance. Okay, and here, so this pier sort of usually is used to protect the port from very energetic waves. So the question is, if, you know, we are seeing the port from above, right? So if this is open sea and there are some waves coming in from the open ocean, what happens when these waves come into the harbor? Like if you are watching the harbor from right above, from a helicopter or whatever, and you're looking, you're measuring, you're taking pictures of the form of the wave. You know, imagine there's a big tsunami wave that's coming in. What happens when the wave hits this opening? Well, I can probably tell you, and you probably can imagine that already. What you would observe is something like this, right? Okay, so what we have here in the open sea is what we call a plane wave. The crests of a plane wave form, if looked from above, a straight line, okay? In the real world, a plane wave doesn't really exist because whatever your source is, it cannot be like to generate a plane wave, a disturbance that means motion of the entire space along a straight line, you would need an infinite source, right? But if you're very far from the source, it doesn't matter because the circular wavefront is so, the curvature is so large that it looks like it's flat. It looks like it looks like it is straight. Okay, so in the first approximation, we can think of this guy, of this tsunami that's coming in, as something straight, as something flat and parallel to the shore. But when this hits a relatively small opening, obviously it cannot continue to propagate like this. We are assuming, of course, that these protections here, these piers, are completely opaque to the waves, right? The water vibrations do not transmit that much into the concrete, the rocks, whatever, that form these structures. They don't move, and so the energy will not propagate through them, but energy does propagate through this structure here. Now, if you think of propagation in terms of Huygens principle, what I have just drawn makes perfect sense, right? Because what we have here, according to Huygens principle, when the plane wave arrives here, well, here we have an infinity of closely spaced secondary sources that each emit a circular wave around themselves. By interference, what I get here is the combination of all those circular waves, and it does look like a plane wave, but on the sides, I only have the contribution from the few sources that are near the ends of the opening, right? So the waveform becomes curved. And what you observe as a whole is a combination of a plane and two circular waves. Okay, so the phenomenon that takes place here is called diffraction. The difficulty with diffraction is that you probably have taken some of you might have taken a little bit of acoustic seismology, whatever. If you think of wave propagation in terms of what we call the array, a path, like a line that describes the trajectory of sound or of the seismic wave, with diffraction, that doesn't work anymore. Because from this point, you have an infinity of ray paths that go into all directions on that side. Okay? So to have a full description of wave propagation, the ray paths approach is not enough. When, and I think people like Young and again Fresnel started to do their experiments, they were working with light, okay, not with sound, using openings, using slits. They observed diffraction and they started observing this kind of phenomena. And that's basically what ended Newton's idea that light was made of particles. If you know, this happens with light as well. And if, as Newton thought, light was made of like little atoms, little molecules that travel the harm, how do you explain this effect? Like, I mean, the atom that is here, how can it go through this direction at the same time? It doesn't make sense. So if you don't have to, okay? You don't have to, but if you're really curious about these things, you can Google Young's two-slit experiment, and that is an interesting take on the meaning of diffraction from the point of view of optics. It's 12:33. We are late, so I don't have time to take your questions now. But please, we are meeting again on Wednesday. Come with your questions ready, and we will take it from here. Okay, I will quickly let you go because you have stuff to do. Okay, unless there's anything really urgent that you want to say. Bye-bye. Thank you.